Okay, so class number 3 is using science to teach math concepts. And I really think that you guys will find a lot of cool activity ideas in here that you're going to want to replicate and use in your classroom. And so I think that this is probably going to be one of your favorite sessions from day number 1. All right, so what I've done is I've gone through the West Virginia Next Gen math standards for K through 5 and also used my knowledge of the K through 5 science standards and also my experiences in the science field to create this list. And so this is a list of very common math concepts that can be used to science application purposes. So whenever you're thinking of an idea for a math activity that you do that you'd like to incorporate some science into, if it's something on one of these topics, it's going to be more suitable for your students and have a longer lasting impression for them. And so these are things that students also struggle with. Whenever I'm teaching college classes, incoming freshmen, the math that they struggle in is actually what prevents them from doing their best in the science fields, right? They understand the science content, but they can't apply the math principles to actually perform the science and to understand the higher level content. And so this is a list of things that you could also work on to make your students stronger in math as you're teaching throughout the year. And so here's the list. I'll read it all out to you. Group greater than, less than, and or equal tos are big in science. Identifying measurable attributes such as width, height, weight, length. Counting the number of objects in a category. Addition and subtraction involved in situations where the sign of the value indicates the direction of the change, whether it's a positive change or a negative change, which we see a lot in physics whenever we're doing vector quantities and adding those vectors together, which I'll have an example of that in this session. Place value in the metric system go hand in hand. You'd be surprised how many students actually have a poor understanding of place value, and because of that, they don't understand how to manipulate the metric system correctly. And so these things are interchangeable concepts that students need to get comfortable with. Equivalent statements. So converting from the English unit system to metric unit system is big, and also just within the metric system, converting, which relates back to place value again, and understanding that the metric prefixes are indicating a particular place value for a measurement. Fractions are huge for everybody. They're so hard to understand, to manipulate, and work with, and relating those fractions to the true value of something, and also representing those fractions in ratio formats are something that students don't instinctively represent as being the same type of value, but is very important to understand. I also have a couple examples of surface area and volume for you in this session. And then we have relating fractional values to decimal format and also therefore to percentages. And in terms of geometry, angles and symmetry are huge in science fields. I know that we use angles a lot in light ray diagrams. In terms of symmetry, we look at the chirality of molecules and use that to help us determine properties of that molecule, which is super important in a chemistry sense. And then we also have grouping. So having different things in a particular group and then being able to represent those in a larger group setting whenever you're analyzing data is something that is important for science application of math. And then constant rates of change is a huge one. This is something that we start developing right from the beginning in elementary school, whenever we learn to count by 2s or to count by 5s or to count by 4s. And so we'll start off with an example on constant rates of change on the next slide. Multiplication and division involved in scaling things, so dilating things up like in geometry class or shrinking them down to a smaller size. Ratios are huge, as I've mentioned probably 5 times on this one slide. And then scientific notation is something that students don't understand. How to write a number in scientific notation, how to convert that number in their mind mentally into a value and relate those values to one another, which one's greater than, less than, or equal to, what magnitude is that measurement that I'm looking at. And then additionally, they actually don't know how to use it in a calculator. So when they're adding, subtracting, multiplying, and dividing, numbers that are written in scientific notation. It just is kind of not there in their wheelhouse. Okay, and so for the constant rates of change, we're going to talk about this physics activity that allows you to address constant speed versus constant acceleration, where when we talk about constant acceleration, we're talking about an object that increases its speed at a constant rate. And so it goes from 2 meters per second to 4 meters per second to 6 meters per second to 8 meters per second. Whereas when we talk about constant speed, we mean that the object stays the same speed the entire time. So it stays at 2 meters per second the entire time. That means you have no acceleration. And so this is a really good physics application of speed of the bubble, where we're going to talk about rates of change. And so you can get this kit from Flynn Scientific by clicking this link. And in the kit, you will get 3 different viscosity tubes that have different fluids in them, and each fluid has its unique viscosity. And that causes the bubble to rise through it at a different rate. And so this is a really fun physical science activity on viscosity. And so what you're going to do is use a meter stick and/or a marker to track the movement of a bubble. And so you can mark the tubes off to know the distance that the bubbles traveled, or you can just or hold a meter stick next to it while the bubble's rising. Have the students decide if they're going to track movement from the top of the bubble, from the bottom of the bubble, or from the middle of the bubble as a reference point, right? They need to make sure that that part of the bubble is the same for both starting the time and ending the time, or you're not going to get a very good measurement. And so students will either completely flip over the tube or just tilt it at a particular angle, which is best done if you have a device to slide it into to keep it at that angle. And then they're just going to measure how far the bubble travels in 2 seconds, 4 seconds, 6 seconds, and 8 seconds. And then record that information in the data table, one for the blue tube, one for the red tube, one for the green tube. Okay, and so if you want something virtual, you can actually use a PHET simulation called the Moving Man. So just a second while I get it saved on my computer. Get it opened up. Okay, so here we go. We've got the simulation now. And you can actually turn the walls off. I highly recommend closing out the walls for this activity. And then you're going to want to go to the charts tab also. So I'm going to have to close the walls again. So the chart tab allows you to see the graphical display while you're doing this. And I really don't need the velocity one or the acceleration one. I really just want to see the position time graph, where I have time across the bottom in seconds, and then position on the vertical axis here. And so I'm just going to start at 0. Oh, I do need the velocity because I have to set the velocity. So let's say I want to have the man move at 2 meters per second. I can set that, and then I'm going to hide this. And I'm going to press play, and it's going to record his movement. I'm just going to let it go. Now, he does go off the screen after 10 meters, but it does continue to collect information. And so I'm going to go all the way up to like at least 10 seconds. There we go. And so after you've pressed pause, you can change this to playback. So that way you can scroll anywhere you want along this line and get information to put into a data table, right? So if I want to see what it was exactly 2 seconds after the man started moving, I can move the cursor to 2 seconds, and then I can round this to 4.0 meters, and I can continue to 4, and I can round this to 8 meters, which if I position it exactly at the 4 second mark, it will automatically go to 8 meters. I can also change the scaling on the graph with the plus and minus buttons. And so students could then use this website to do a similar activity as the speed of the bubble. And they could turn their data table into a graphical display where the graph will fit completely on the graph sheet of paper. And then you can also play around with changing the velocities of the man. And so that way you get different slopes and see how he was traveling faster depending on the velocity you set it at. You can also do things with acceleration if you really want. So I also thought of a really fun, engaging way that you could probably do this on a field day or before field day, or if you're a gym teacher and you're maybe wanting to incorporate some science into your gym lessons, your gym time lessons. You can kind of like mimic this. Keep in mind that the constant rate of change is the key point here, right? So if I'm traveling at a speed at 2 centimeters per second, then each second my value is going to go up by 2. So it's like I'm counting by 2s. And so we asked the question, well, let's make a prediction. How many centimeters will the moving man have walked after walking at this speed for 5 seconds? So we could then follow this pattern to add 2 more centimeters and get a measurement of 10 centimeters as the total distance. And then what if we change the man speed to 5 meters per second? Can we make a prediction on what his distance values would be? And so for gym class, something that you could do, or if you are just outside someday, you can let your kids act it out instead of using the virtual simulation. You can set up a straight line course and mark it per meter with some type of flag that you can put in the ground or some kind of marker you can lay on the ground, and then give students different colors of place markers depending on the speed they're going to travel. So for example, if I have a group of kids that I want to move 3 meters each time that I clap my hands, I'm going to give them the green markers, and each time, each group that's going to move maybe 1 meter each time that I clap my hands, I'm going to give them the purple marker, and so forth. And so those students can then practice their running and then stopping after you've clapped your hand, and then do another clap and show them how they are going to have to change their speed to make it to that marker in time. And so they'll get a real life feeling for what speed is and what it means to be traveling at a higher speed and at a lower speed. And plus they get to run around, which you know they love. And so you can end this with all right, let's have a 50-meter dash. Or you can require them to keep their constant speed until they reach the end of the 50 meters and see who makes it there first. Okay, so let's move on to another math concept, surface area and volume. And so this little video I created explains a lot of different ways that you can do this melting of ice cube activity, which I read about for the very first time in an NSTA article, the National Science Teachers Association organization, which was written by Moyer and Everett. And so this is just a bunch of different ways that I decided to do the same activity.
Start by measuring 2 cups of water per Rubbermaid container and then freeze both. This ensures that both blocks of ice are the same volume. Now, at the same exact time, put them both in a Ziploc bag and take one and crush it by dropping it on the floor. Because the crushed ice has more surfaces, this sample has more surface area. Prepare 2 large bowls with 4 cups of water and some food coloring. Try to get the same amount of food coloring in each. Using a thermometer, check to make sure that the temperature of each solution is exactly the same before beginning. It's best if you have 2 identical thermometers. That way you can leave them in the container throughout the experiment. With the help of a trusty volunteer, put the ice samples in the bowls at the exact same time. And then record the temperature every couple of minutes at the same exact time and report your information in a data table. Just a few minutes in, sample number 1 is down to about 68 degrees Fahrenheit, while sample number 2, the one with crushed ice, is down to about 59 degrees Fahrenheit. Continue to observe until one of the samples has completely melted. Which one do you think will melt first? If you want each of your students to participate, you could use a popsicle mold so that you have enough ice chunks for each student. I've even gone as far as making my own ice cube trays using plastic binder dividers and letting students measure the surface area of each side before they tape them together. But Amazon has these really great trays that you can use scissors to cut out each piece and do something very similar to what I'm about to show you. color one side of your ice cube tray with a magic marker and then press it down against a sheet of graph paper. This will allow you to count the number of squares and get a pretty accurate measurement for the surface area of each side. Do this for each side and then add them up to get the total surface area for your ice cube. You're using a sheet of graph paper that's marked in centimeters squared, then you'll be able to count by each square to get this total surface area for each ice cube in centimeters squared. Continue to add that surface area for each ice cube that you have that you're going to use in the experiment. You can even use irregular shaped objects if you want. It's a little bit more challenging, but you can still get the surface area for the ice cube tray after you cut it out. I do recommend that you use regular rectangles and squares. As you can tell, it's going to get a little bit harder to get the exact number of squares for each side. And so this is going to introduce error into your measurements. Try a couple of different techniques. Maybe you'll find one that you like. Start by measuring 2 cups of water.
Okay, so this is the graph that I created using chartgo.com, and you can see how the broken ice cube rapidly decreased the temperature of the water and then leveled off, whereas the whole ice cube took some time before it started lowering the temperature of the water, but then it also finally reached a point where it leveled off. And so I've also put on some lines of best fit to kind of show the exact average of the change in temperature that occurred depending on the surface area. And so why does this phenomenon happen? Why does the increased surface area cause for cooling? Well, if you take a look here at just these squares that I drew, or rectangles that I drew, notice how the one that's longer and has more surface area had more red arrows that I could put at equal spaces around the shape than the one that only has 12 red arrows around it. And so by getting more surface area, I have more places of contact where a heat transfer can take place. And so the heat of the water can be absorbed by the ice to help melt the ice, which in turn cools the temperature of the water. And so by having more surface contact points, the heat exchange process happens at an accelerated rate. And so there's another example here for surface area, and that's with a particular leaf collection, which some of you may already be doing with your students. And so if you just have them have a centimeter grid of graph paper and use the leaves that they collect to draw or outline the leaf, and then actually count the number of squares to determine the surface area. And so why is surface area important whenever we're investigating leaves? Well, the leaves of plants are actually the most important organs that they have. This is where photosynthesis occurs. So sunlight is absorbed in by chloroplasts, and then the stomata, which are openings on the underside of leaves, actually open up and allow carbon dioxide to be pulled in from the air to allow for photosynthesis to take place. Now also, water can also be released through the stomata of these plants. And so there has to be a regulation between how much water leaves and how much water is retained while carbon dioxide is pulled in from the outside air. And so plants will modify the surface area of their leaves depending on the type of environment that they're in. And so to regulate this amount of water that's within the leaf, anywhere that's drier or where there's not much rainfall, like high up in canopies where the sunlight is abundant, and also where temperatures are highest, leaves will be smaller, because decreasing the surface area means that whenever those stomata open up, less water will come out at one particular time. And so we see the opposite in the wetter areas, so like in a low canopy setting, or where there's less light, or in places where there's lower temperatures, the leaves are larger because there's going to be much more water available for them, so that they can pull water up through their roots and replace the water that was left whenever the stomata of the leaves were opened up. And so places where there's not a lot of moisture content in the soil, they're not going to have that advantage. And so the leaf surface area will change because of that balance that's needed to keep the plant healthy. All right, let's move on to another math concept. So place value, and how you can teach place value using volume measurements and incorporate the metric system at the same time. And so what you're going to want for this is red, blue, green, and yellow food coloring. You're going to want a 10 milliliter graduated cylinder, 100 milliliter graduated cylinder, and 1 liter graduated cylinder per group or student, depending on how you're going to lead the activity. And so to get those graduated cylinders in a plastic form, I suggest these, which are what you can buy from Discount School Supply. They actually have a lot more than what you need, but they also have the 10, the 100, and the 1 liter. And I'm picking the 10, the 100, and the 1 liter because each one represents a different place value, right? Where 10 milliliters is one place value, 100 milliliters is the next place value, and 1 liter or 1,000 milliliters is another place value different. And so this is a really nice way to teach place value, or to reinforce place value. So plastic containers you're going to want for each group so that kids can mix their colors together. It doesn't have to be graduated with volumetric markings, but it could just be an empty or an unmarked container that's see-through, so that after the students mix their colors together, they can look at what they've created. And then you're also going to want plastic containers that can dispense large amounts of your colored solutions, because you're going to prepare those ahead of time. And so for the procedure, the first thing you want to do before class starts is prepare ahead of time your stock solutions of each color. And so you want a big amount, so that way students can decide whichever colors they want to use. And so you can put it in a container that's dispensable, so students can just walk up, pull the lever, and get the color solution out if they want. And then their kids aren't even messing with the food coloring drops at that point. You're just putting in the number of drops ahead of time in your stock solution. So get them the color you like, and then leave them in those dispensers for kids to safely come up and get their solutions from later on. Okay, and so after you've prepared your solutions, you're going to demonstrate color mixing to your class. So you could, for example, mix 10 milliliters of the red and 10 milliliters of the yellow solution. Show them how to measure out the solution in the graduated cylinders. Remember, you're going to have to use the bottom of the meniscus, or the U shape that forms at the top of the liquid. And that's due to surface tension, where molecules are adhering to the edge of the plastic. So you're going to see a little dip. Read from the bottom of the dip and make that bottom line up with the 10 milliliter mark. And then mix them together in a big bowl, and in a bigger container, and show students how the color changes whenever you mix them together. And so you can continue with, well, what happens when you mix a 100 milliliter of the same color with a 100 milliliter of the yellow solution? You would ideally get the same color, you're just going to have a larger amount of it. And so you can leave those on display, and then give students the opportunity now to see what happens when you change the place value of the color that you use. So what happens when you mix 100 milliliters red with only 10 milliliter yellow? And so you'll see that one of those colors will dominate, and you won't get the same exact color. Instead, you're going to get a color that's closer to the red than it is the orange that it would be whenever it's mixed together. And so describe to students if this is the dominant color. Red is dominant because it's 100 milliliters, and so we're in the hundreds place value, whereas with the yellow mixture, we're only at 10 milliliters, which is the tens place value. So there's a lot less of it there. Okay, and so then you're going to provide students with directions for safely going after their color solutions, and then also give them the data sheet to record their color mixing. And so I've made a little version of a sheet that you could use. It's very general and could be adapted, and you're welcome to change this. But I put a color wheel in here for color comparison. I've given some directions. So carefully pour the correct volume of color solution into your graduated cylinder and move it to your workspace. At your workspace, write down the colored solutions you're going to mix and the amount that you're going to mix. Then mix the colored solutions into the mixing container to see the result. Clean out the mixing container before you reuse it. And so here's a particular example. A student might want to mix yellow and blue, but they're going to use 80 milliliters of the yellow and only 5 milliliters of the blue. And so we've got a tens and a one place value combination. And so when we add them together, we get a total volume of 85 milliliters. And our final color is going to be something like the chartreuse here, because I'm using so much yellow and only a little bit of blue. It's only going to slightly change the color to chartreuse. So it's really neat to kind of show that to students. And so I've just made a spot here where they can make their own color combinations and report the values and the information in the table. And then there are some questions that begin. Which number trial resulted in your favorite color? The color was what? Which color, red or yellow, would dominate the color mixture if you mixed 800 milliliters of red with 40 milliliters of yellow? And so what color would dominate? Obviously, it's going to be red. What would the total volume be if you mix 600 milliliters of green, 20 milliliters of red, and 4 milliliters of yellow? Show your work. And then they will report their answer here. And then it says, name the place value of the number 2 in the measurement. So this is the tens place. Name the place value of the number 6 in the measurement. Well, that's the hundredths place. Which color would have which color would you have the least of when mixing 600 milliliters, 20 milliliters of red, and then 4 milliliters of yellow? Well, you're going to have the least of yellow. So which color do you think would dominate this mixture? That would be the one that you have the most of, the green. And so ask your teacher to mix the colors together from question 6. Predict the final color of the mixture. And then they would probably go back to their wheel here and decide, well, it's got to be close to green because we're not putting a lot of other stuff in it. And then what was the actual color after the teacher mixes it together? And so also, I'm visualizing you going further with this and extending it after the kids have a chance to explore with that activity. And so what you're going to do is then do a demonstration for them. And so you're going to take the unmarked side of your 10 milliliter graduated cylinder, and instead of marking it by milliliters, we're going to write in permanent marker 1 centiliter. And then you're going to add 1 milliliter from another cylinder at a time to your new marker and demonstrate that it takes 10 different milliliters to completely fill up the marking to 1 centiliter. And so then you're going to record this on a classroom chart, which will look something like this whenever you're finished. And then how many milliliters then can make up a deciliter? So you're going to do the same thing, but you're going to take a 100 milliliters cylinder that's on an unmarked side and mark the top line as being a deciliter. And then how many centiliters, so of your container that you just used with the new marking on it, add that one by one, and you'll see that, wow, it takes 10 more to fill this up. And then how many milliliters will make up a liter? So using your 100 milliliter graduated cylinder, we're going to mark it on one side as a liter, and then you can add your centiliters to figure out how many centiliters make up a liter. And also you're going to do the same thing with your deciliter marked cylinder to determine how many of those will make up a liter. And so it'll be 10 deciliters makes 1 liter, 100 centiliters will make 1 liter. And so this is a good way to start addressing equivalencies and place value at the same time. And so you'll report your information, and of course you'll fill this in block by block. So of course 1 liter is 1 liter. Well, it's going to take 10 deciliters to give you 1 liter, and it takes 100 centiliters to make 1 liter. And then it takes 1,000 milliliters to make 1 liter. And then you could do the same thing with deciliters. Well, how many centiliters does it take to make 1 deciliter? It's going to take 10. It's going to take 100 milliliters to make 1 deciliter. And then if we make the centiliter our unit for comparison, we're going to need 10 of those. And so you really are going to work your way from the bottom up here. So if you do it in the correct order, how many times is it going to take me to fill up a centiliter? It's going to take me 10. Well, what if I want to fill up a deciliter? Well, it's going to take me 10 centiliters, and it's going to take me 100 milliliters. And so you're going to have this discussion question. Well, which unit? A liter, deciliter, centiliter, or milliliter is actually the smallest. So this is the smallest unit of measurement, whereas a liter is the largest unit of measurement. And you'll notice that the metric system is heavily reliant on place values. So we're just changing numbers here by a factor of 10 each time. And so to blend your place value and the metric system together, let's break down the following measurement into liters, deciliters, centiliters, and milliliters. And so keep in mind that the prefixes of the metric system tell us which place value. So deci means a tenth of something. So that's why whenever we had a liter, a deciliter required us to have 10, because we need 10 tenths of a liter to make an entire liter. And so centi means hundredth, so that's why I need 100 hundredths to make 1 entire liter. Milli means thousandth in the metric system, and so we need 1,000 thousandths to make 1 entire liter. And so if I have 3.420 liters, how many liters do I have? Well, I actually have 3 whole liters. I have 4 deciliters. Notice different place value. This is in the tenths place value. So that's 4 tenths of a liter, or 4 deciliters. I have 2 hundredths of a liter represented here. So that's going to be 2 centiliters. And I have no thousands, so just 0 milliliters. And so I can report this as 3 liters, 4 deciliters, and 2 centiliters. Or if I just want to keep things in terms of the smallest unit that I'm using with the graduated cylinders that's marked, would be reporting it in milliliters. So that's 3,000 milliliters, 400 milliliters, and then 20 milliliters. Added together will give us the 3.420 liters. And so then you can apply your students' knowledge now of place value and the meaning of the metric prefixes to see if they are really catching the point here. So here's a good application question that you could ask later on. Well, which color would dominate the mixture of blue, red, and yellow if I had 2 deciliters of blue, 6 centiliters of red, and 4 milliliters of yellow? Well, then this is going to force students to think a little bit about the meaning of these prefixes. Deci means tenth, centi means hundredth, and milli means thousand. So even though 6 is the largest value, centi is not the largest unit that's represented here by centiliters. It's the deciliter. This is a tenth of a liter, whereas centi is a hundredth. And so 6 hundredths of a liter is only 0.06 liters, whereas 2 deciliters would be 0.2 liters. And so the answer here is blue is going to dominate. And then you could mix it together and show them the color. And so what would the total volume be in milliliters? Well, if this is deciliters, I'm going to have to change this to 100 milliliters. So 200 milliliters plus 60 milliliters plus the remaining milliliters from the yellow would give you your total volume there of 264 milliliters. So what would the total volume be then in liters? And so again, this is going to be a tenths place. So this is going to be 0.264 liters. You could do a couple of practice activities like that to give them the experience. And then doing the color mixing is going to be a really engaging thing that they're going to want to try out and see what the colors are. And so you can use that as kind of a motivation. Well, if you get this problem done and working together, if we can get through this, we'll mix these colors together and see what they create. And you can help me maybe. Okay, moving on to another topic here. I talked about using the signs of addition and subtraction to help us come up with a sense of direction. We're talking about vectors. Well, we already taken a look today at the tug-of-war simulation on the phet.colorado.edu website. And this is a perfect example of exactly what I mean, right? So if we're in a situation where this person's adding 100 newtons of force to the right, well, then the person in blue is actually subtracting 50 newtons off of that applied force because they're putting it in the opposite direction. And so this will give us a sum of 50 newtons in the positive direction, which is into the right. And that's what is known as our net force. The sum, or the result here of putting all of these vectors together by adding them or subtracting them out. And so here's another situation. We've got 200 newtons of force in the negative direction. So we're going to subtract that off of the 100 newtons in the positive direction. And so 100 minus 200 is negative 100. So our net force is now 100 newtons to the left. Or you could see this in the reverse. You could do negative 200 newtons as the applied force, and you're adding 100 newtons in the other direction, and it still ends up with the same net force. Okay, so that was plenty of examples. What I want you guys to do now is start your brainstorming, right? Think about what it is that you're teaching in your class when you get back to school, and how could you use science to teach that math concept? And so I want you to select a math concept or an assignment that you routinely teach with your students. It could be fractions, symmetry, etc., anything. It doesn't even have to be on the list I gave you, but if you need some inspiration, use my list. And then I want you to, in your journal post, for journal post number 3, describe your brainstorming, right? You don't have to have the assignment create it. You don't have to make a worksheet like I did for the volume of color mixing. You don't have to do anything super extravagant yet, but this is your brainstorming. I just want a couple of paragraphs on what you think that you could do or what might be interesting for you to try to use science to teach your math concept. Okay, and as always, if you guys have any more questions for me, please email me through fairmontstate.edu, or it's jrevels@fairmontstate.edu. You can email me at my Google address or using the Google Classroom comments as well. So just make sure you stay in touch if you have problems or need help with something, and I'm here to help you. Hope you guys enjoyed this session, and I can't wait to see what you guys come up with for ideas for your classroom.